Great, we're recording. Great, so the stage is all yours.
Okay, thanks for that introduction. I can't share my screen.
Bear with me. Bear with me. Yep. Okay, so can you see now, maybe?
Yep, that's
okay,
good.
Great.
Cool. So can you see my slides?
Yes.
Brilliant. Let me just... Okay, so hi, as Natalia said, my name is Constance Crozier. I'm a postdoc at CU Boulder, and I'm going to talk today about my experience as as the developer of one of the teams in the recent ARPA-E Go competition. So the Go competition is a multi-million-dollar initiative started by ARPA-E to facilitate development of faster and smarter power grid optimization software. So this is looking at transmission system optimization, and the first two challenges have focused on security constrained optimal power flow. But I'll talk more about the formulation later. The Electric Stampede team is a collaborative team between CU Boulder and UT Austin. Kyrie Baker and Javad Mohammadi are the principal investigators on they won one of the seed grants for the first competition, and I'm employed using the prize money that they won in the last challenge. I didn't work on challenge 1. Some interesting things about our team is that we're one of the only power systems teams that did well. Most of the teams came from optimization backgrounds, and a lot of them were actually companies rather than from universities. I can't really make any comments about why that might be. We're also the only female-led team, which, in fact, depressingly, our team includes 2 of the only 3 women competitors in the Challenge 2 competition. So I'm going to talk a bit about the problem formulation. I kind of assumed that everyone, given the focus of this group, would know what optimal power flow is. I should have said at the start, I'm happy for people to just interrupt if there's major questions or something that I say that's confusing. But I mean, if you don't know, optimal power flow is just finding the cheapest way to operate electricity grid. In this case, this is a transmission network. So looking at just the high and medium voltage components and the pooled generation and load at each bus. So SCOPF is a 2-stage stochastic optimization program that's an extension of the optimal power flow. We consider sort of 3 periods of time. We consider the initial commitment, which is the position that the network is in at the starting point, at the point that you get it. In the competition, they called it the initial commitment phase. You can also think about this as being sort of where at the end of the electricity market process, what the planned operation of the grid might be. At the start of the competition, the initial commitment state was a balanced power flow solution, but they also did introduce some cases where the network started not in a physical state. Then you have what's called the base case time period. This is the time that you're planning for. So the time between the initial commitment point of the network and when you're actually planning to operate it for that time instant. And it's called the base case because this assumes that nothing has gone wrong. There's been no component failures or contingencies. And then at some time later, we consider the network in a large number of states where in the Go competition, it was only ever one component, but there's been one component failure. It's called N-1 SCOPF. N-2 is when you also consider 2 component failures. And that's a step in time later because you have this time to respond to after an event is happening. I think I've got, yeah. So there are two types of SCOPF. There's what's called the preventative solution, where, and I should have said that there's time rampings on a lot of the controls of the problem, specifically the generators. We can't alter generator output very significantly in a short time period. So what you pick for your base case operation has usually quite a large effect on the kind of contingency operation you can achieve. So there are two kinds of SCOPF. There's preventative SCOPF, which is mostly what I'm going to talk about today. This is finding a base case solution, given your knowledge of all of the contingencies, the component outages that could occur, finding the base case solution that is optimal in a stochastic sense. So not just the cheapest possible base case solution, but the cheapest possible base case solution, given that we also might experience any of these contingencies. And that ends up being a very large optimization problem, because you have to consider, you have a set of network variables for each K. In this case, I should say, there's the index I'm using for the contingencies. So K0 is the base case, K1, 2, 3, 4, N are the contingency cases. And for each of these, we'll have a set of network variables. So network voltages, magnitude and angle, all the generator real and reactive outputs, the loads. I'll talk more about the specific variables later, but there are a large number, and you have to have a set included for your optimization problem for each contingency. You also have a set of power flow constraints for each contingency. So the computational complexity of preventative SCOPF is very high. And corrective is working out the network operation that you're going to achieve for if any of those contingencies happen after you've picked your base case. So this is the second stage of the program. This you do after you've picked your base case solution. You want to have the a kind of contingency plan, if you will, for each of the contingencies. And this basically is just an optimal power, a regular optimal power flow calculation that you have to do n times, where n is your number of contingencies. And you can do it in parallel, because it doesn't, there's no interplay between the contingencies. They're only affected by the base case. So for the Go Challenge 2 formulation, I'm just going to talk about some especially interesting points of it. I'm not going to go through the whole thing. The whole document you can look up if you like. It's 97 pages long, so it takes quite a lot of time to get on top of it. And as you can see from this screenshot, this version of the formulation was published in the end of May 2021, which was actually more than 2/3 of the way through the Challenge 2 of the competition. So they kept not like changing it, but more finding bugs in the formulation as they were going, which was added some, I guess, excitement to the competition as we were going. But yeah, I'm going to talk about some of the biggest things that were different from what you would consider to be like a standard optimal power flow formulation. So the first and maybe biggest thing that this formulation had was this unit commitment. So a lot of optimal power flow formulations, especially on like the IEEE standard networks, you consider all of the generator outputs to be continuous. And it can go sort of often from 0 to a certain number. So you can turn generators off by like just turning their power down to 0. Or there might be some generators that you can't turn off, but normally you just assume that all the generator outputs can be varied continuously between 2 bounds. In this formulation, they had this firstly committed position of each of the generators. So every generator, based on, like I said, the kind of market solution, was committed to be either on or off. And there are ramp rates, like I think I talked about, which are the kind of time linking between the 3 time steps. So the initial time step, the base case, and the contingencies. So this is like for one of the generators, you can imagine that the generator starts at this PG0, and the ramp rates mean that you can turn the generator down to this minimum or up to this maxima. These blocks of marginal cost is how the cost was measured. So a lot of optimal power flow formulations assume linear or quadratic costs for the generators, but that's not very realistic. In this case, they assumed blocks of constant marginal cost, and it was necessarily increasing. So there was like the first bit of power that could be produced was the cheapest, and then there were these blocks, which meant that the actual cost function was piecewise linear. So those are the ramp rates, but the unit commitment allows you to also have this binary decision that you could switch a generator on or off. So to start with on, the committed position of the generator could be that it was at 0, but that there's some minimum output that it actually needs to produce. It can't produce like 0.01 megawatts. It has to produce at least this amount. So you could take this binary decision to switch the generator on, and there was a cost associated with that. And then you get this range of possible generator powers. And perhaps more importantly for the competition, you could also choose to switch some generators off. So we have the same generators before, but we could choose to actually pay this shutdown cost and turn the generator to 0. This turned out to be incredibly valuable because obviously trying to achieve separation between all the teams in the competition, they had some formulations or some networks where they started with a lot of very expensive generators on. So they really didn't want you to just ignore this. And this is like the challenge 1 of the competition didn't include any integer variables. And integer variables really limit the number of solvers that you can use. And this is one set of this particular set of integer variables was kind of, you were sort of damned if you didn't include them. If you just like stuck with the generators which were on, which I think we did for trial 1, it's you really limit your performance mostly because of these very expensive generators that they keep on and the very cheap ones that they decide are committed off. So that was a brief overview of generation. There were also binary variables with the transformer controls. So some transformers had phase shifting controls and some had tap controls, and they were both like integer steps. So I guess that makes more sense with taps. I never really got my head around phase shifting transformers, but to be honest, I'm more of a software kind of person than a hardware kind of person. But all this to say, you had these variables XF that you had to pick, which changed the phase shifting angle or the like transformer tap, which would have been complicated enough, but there was also this transformer impedance correction, which is kind of horrific, which says that in reality, the transformer impedance changes slightly for different phase shift or tap configurations in some transformers. So they have this piecewise linear function that says, you know, for the, say for the phase shift, depending on which of these control positions you're in, you get a different impedance correction. And they typically had this kind of U shape around the central position, in this case, like no phase shift. But sometimes they were kind of complete V's, only 2 points. Sometimes there was like 36 of these. And yeah, as you can imagine, this is like a binary variable, integer variable, sorry, on top of another integer variable. So it's not very friendly computational wise. The next thing they introduced, which was interesting, was some form of price sensitivity for demand. So you had this variable T, which for each load, and there might be several loads on one bus, you can scale the both real and reactive load by the same amount. And again, there is ramping rates on this, both from the unit commitment state and to the final contingencies. So the starting position of T is, I don't want to say always 1, let's say almost always 1. And you have this ramp down or ramp up. And these tended to be pretty generous, actually. There was quite a lot of demand flexibility. I think, again, because they really wanted you to include it, but that actually had some interesting effects on the competition that I'll discuss later. And the way they introduced the demand response aspect is that while in the same way that the generators each had like these constant blocks of marginal cost, the load had constant blocks of marginal benefit that was decreasing. And so you start, and they're again ordered. So you start with the most beneficial block of load. That's the load that you serve first. And you step out. And something that they introduced, I think just to screw with everyone's code, to be honest, later in the competition for some of the networks were these negative benefit loads, which I guess is some form of demand turn up where you pay the consumer to use more load. I don't really like it because we only consider in this competition one time step. So it doesn't really seem that practically realizable. In my opinion, demand response is just like demand shifting, not just paying someone to not use the demand altogether. But yes, it made for a more complicated optimization. Luckily, there were no binary variables associated with demand. You couldn't just disconnect consumers. They probably thought that that was too controversial. But I really appreciated that from a computational perspective. So the computational and time limits. So we could run up to 6 MPI processes with 24 core nodes. I'm not going to talk about the hardware because, again, that's not my area of expertise. I've got a link here so you can visit if you want to see the exact platform that we ran on. But all the code was tested on one piece of hardware that was in PNNL, which is a lab that's in the middle of nowhere in Washington State. I can't remember the name, Pullman, Washington. And for the preventative optimization problem, which is that big problem I talked about with all of the contingencies variables, we only had 5 minutes to solve that, which given that amount of computation was a very short amount of time. In the last challenge, in challenge 1, the problem was completely continuous and had much fewer variables, and they gave you 10 minutes. So I think they were just sort of seeing what we could do in that sort of time. And I think they also anticipated there would be more competitors, and they wanted to limit how long it would take them to test all of the code. The last thing is that the networks were unseen, which meant that we had to design these algorithms without any knowledge of what the network was going to look like. They did this because there were these industry networks, which were supposedly real transmission networks, but due to the infrastructure laws in the US, you're not actually allowed to access those. But it added like a lot of complexity, having to find something that heuristic-wise you could do for literally any unknown network. As the competition went on, it became clear that some of the networks they were reusing again and again in the trials, but with different, more contrived loading scenarios. They didn't like actually announce that, but yeah, it became obvious. And also some of the networks, when you actually looked into the data, were just multiple networks stuck together. But there were these industry networks which we will never have access to. So you could test them on the system, but you couldn't see how many buses were on the network. You couldn't print out any of the data. You couldn't, like, debugging was very difficult on those networks. So now I'm going to talk a bit about, let me just check the time. Okay, about how our team's approach was. So we wrote our code in Python, which was quite controversial because Python is not the fastest language. The team that won was using C++, but quite a lot of the other high-performing teams were using Python. And I think it actually allowed us to test a lot of things more quickly in the earlier parts of the competition. So I don't really regret it. And for solvers, we used two. We used Cplex by IBM, and we also used IP-opt, which is a very old nonlinear solver that almost all of the top performing teams used. It doesn't handle mixed integer variables, but there are actually no mixed integer nonlinear program solvers that you can get with an academic license that I'm aware of. At least, I mean, no team in the competition used one. And yes, I don't think that there are any that do large scale problems, at least. So something that was interesting that I think all of the high performing teams found is that with the way they posed the problem, we could actually decouple the problem. And that means that instead of having to consider this one really large optimization problem with all of these contingencies, we could actually just consider the base case by itself and then just run all of the contingency OPFs separately. And I think ARPA were really unhappy about this, actually. But just because of the way that the scoring worked and because of the demand flexibility, there was so much flexibility on the network that you could recover from even the biggest generator outage just by turning down the demand a lot. And this really, I think, meant that we could achieve more, like focus more on actually solving an OPF for the base case, because we could sort of throw out a lot of the variables. It's kind of funny, actually, one of the things that I thought, because although I know some of the other teams, we didn't really talk about our approaches for obvious reasons. And I think everyone thought that they were the only one that had thrown out all the contingencies. But when we all spoke about it after the competition, I think all of the top 6 performing teams had decoupled the problem. So we also removed a lot of the things from the formulation that we either couldn't do or that we found didn't make a really big difference to the score. So something I didn't talk about is that there were also integer shunt controls. So there were some switch shunts where you could add sort of blocks of reactive power. And they tended to be like really big blocks, which meant that relaxing them to be like continuous didn't work very well. And we found that we tried some rounding approaches, but they weren't very stable. So in the end, we just kept the shunts in their starting position, and the same with the transformers for the same reason. They also had optimal transmission switching in the problem for 2 of the divisions. And we spent a lot of time trying to get this to work. But I think in the end, the highest scores in the line switching divisions ended up being the same or lower than the scores in where you had to keep the lines where they started. I'm not going to say that optimal transmission switching doesn't work, but I don't know. I'm sure it works in some cases, but I think that just with the time that we had, people couldn't solve a problem that was that big. So how did we actually do it? So in order to get this unit commitment, which, as I said, was this generator thing, it's really important that we were able to turn off those really expensive generators. We took a 2-stage approach where we developed a MILP formulation of the SCAPF problem with Cplex. This allowed us to switch on and off generators with linearized cost function. And we had the binary switching costs. We had to use the DCOPF constraints. We tried a bunch of other linearizations, and we found a lot which were more optimal in some cases, but we didn't find any that was quite as fast and stable as DCOPF. So we ended up sticking with that. And you can't just run a DCOPF for this competition because you have to submit a complete power flow solution. So you have to submit the voltage magnitudes, angles, reactive power, lots of things that aren't in DCOPF. So then we had this IPOps, this continuous nonlinear program, which uses the AC power flow constraints. We do run another OPF, so we don't stick to our generator outputs from the DC because you'd have to turn down the loads because DC is lossless. We mostly used, apart from the simplifications I talked about, the full formulation because we'd thrown out the contingencies, so we had time. And that output our base case solution. And then, yeah, I should say that this second block is just what we use for the corrective SCAPF. We just run a bunch of power flows with the same code. So I think one of the strong points of our approach is that we ended up with a really fast code, which was kind of, I think our code was actually, we were told, finished the fastest on many of the networks in the final event, which is kind of funny because we got all this like crap for writing our code in Python. But the main way that we achieved that was by deriving analytical formulations for the Jacobian and Hessian in IPOpt. I don't know if anyone's directly interfaced with IPOpt before, but so you can interface with one of these. We used Pyoma at first. So you formulate your problem in Pyoma, it just like formulates it. It does all of the under the table work with the solver, and it just magically somehow works. But it's pretty slow because it uses approximations for the second derivatives. There's also a huge overhead time with Pyoma because when you formulate in Pyoma, it doesn't yet know which solver you're going to use. So it's in a solver invariant way. It was definitely very useful to do that first because we could try, it was easy to switch in and out solvers. Yeah, in the first trial, I think, despite not doing that badly in the rankings, our code timed out on the vast majority of the networks, which just goes to show what the general standard was like in the first trial. But yeah, I spent a lot of painful time deriving analytical formulations for the Jacobian and Hessian of the problem, and you have to implement it in IPOpt. Given that it was calculated in Python, if you do it in loops, it will still be slower because there's this trade-off because yes, you'll converge faster because you have the analytical formulations, but if each step where it's calculating these matrices is slow, then because each iteration is slower, you can actually end up making a slower code. So it's really important to be as smart as possible with the way that we were formulating these matrices, formulating them as in vectorized form as NumPy arrays, and only converting to lists at the final stage, which is what the form that IPOpt wanted. So something I also didn't mention earlier is that in the formulation, there were these slack variables. And at first, I think this was their way of not failing people for having bugs, but just them paying large cost penalties. So if you submitted a code that wasn't a valid OPF power flow solution, there were these slack variables which allowed small imbalances at each of the buses, but you paid a really high price for them. I thought that was the only reason, but throughout nearer the end of the competition, there were a couple of scenarios where they produced networks where there was no feasible solution, and you just had to find the closest to feasible solution, which is definitely just a trick they were playing to try and achieve separation, because that's not really a practical real world implementation of that. There were also slack variables on the lines, which allowed you to kind of override the thermal limits a bit and just pay a penalty. In general, I didn't find any case where it was actually worth paying even like the smallest penalty. If you treated the constraints as hard, in general, you still got the same solution. So for our AC code, to speed it up, at first we did treat all of the constraints as hard, not soft. And we let the code run for 75% of the time it had allowed. And if it still hadn't converged, we had this backup code that just tried to find the nearest feasible point. This was mostly for the contingencies, because in the contingencies, there were a few cases where, depending on the base case you picked, you might end up with one contingency where the network wasn't in a physical state. But because the penalty that you paid on the average contingency price, and sometimes there were thousands of contingencies, it ended up not actually meaningfully contributing to your score as long as you were in a kind of close to feasible position. So on the worst networks, this happened maybe like 1 in 100 contingencies, but you don't want to pay, $100 million penalty in one of the networks, because if you divide by 1,000, that's still a really big number. So we did the code with the hard constraints, and if after 75% of the allotted time it still hadn't found a solution, we just ran this backup code that just says like, okay, this is a bad contingency, just try and find something that's as near feasible as possible. And this allowed us to finish in time. I think from trial 3 and for the final event, we didn't time out in any, in the last 2 events, we didn't time out, and we finished on time in literally every scenario of every network. So we did achieve a fast code, only that. So just to talk a bit about kind of my reflections on how our approach worked. So these were our rankings throughout all of the events. I talked before about trial event 1, how we timed out in almost every network, but we still came like well in the top half. But I think in trial event 1, everything was about trying to find this feasible solution. And a lot of people's code was not finishing in time, or was just like had bugs to the point it didn't find it. In fact, some of the teams that did really well in all 3 trials got 0 because they had a really ambitious approach, but they just weren't quite being able to find these feasible solutions in time. So between trial 1 and trial 2, we really focused on speed. That's when we implemented all of the analytical solvers, switching from using Pyomo, all these things that focused on speed of our code. Trial 3 was our peak performance. So in between trial 2 and trial 3, this is where we were looking at the cases that we did badly in trial 2, which were these edge cases, the cases where there wasn't any feasible solution, or where there were these negative loads. So we tried to focused on the robustness of our approach to try and make sure that we would find this feasible solution in any case. There was a very short event, gap in time between trial 3 and the final event. So we didn't do that much in between that. We did kind of tuning of the parameters in terms of how long we were letting each code run, and some trying to debug the couple of networks that we had bugs in from trial 3. But we did really significantly worse. And that was partly because the scores for the final event ended up being very kind of flat there was a very clear winner, but then sort of positions 3 through 6 were very flat in terms of difference in score. Because everyone would kind of, I think, had been focused on this feasibility thing as they were going through. And in the end, what got us was one, that we had a couple of networks where we had a bug. So we got 0 in those networks, which obviously, when the gap was really big, brought us down quite a long way in the leaderboard. And the other was this two-stage approach that we did with the DCOPF. And let's say a third of the networks, that doesn't work because the DCOPF picks a solution for which you can't, there's no solution that doesn't violate the voltage bounds in terms of those generators being on. And for those, in those cases, we ran a backup code in parallel that just stuck with the generators that were on already. But then we hit this problem with these really expensive generators being on. And yeah, I think that was like our main downfall in the final event, is that everyone else had, like, I think we were sort of leading the way with developing a really fast and robust code, but we sort of lost sight of optimality, and the other teams sort of caught up with us as we went along. But, you know, hindsight's 2020. And so reflections on the whole competition. This is just my thoughts about kind of what was good and what was bad. So with the computational power that they gave us, 5 minutes was sort of ridiculous. If we hadn't been able to decouple the problem, I'm not sure what anyone would have done. But even though we could decouple the problem, 5 minutes wasn't enough for optimality with these binary variables. And up to 31,000, I think in one case 34,000 actually buses. That was like not sufficient to actually find an optimal solution. The trial events were really valuable. There were some teams that kind of were, I think, afraid of performing badly in the trial events and looking bad, and so just didn't participate until the end. And almost without exception, those teams did really badly in the final event. I think the trial events were really useful. The private network thing, this industry network, was perhaps the worst part of the competition, especially because the data, like there was a lot, the data was in a slightly different format, and there would sometimes be like missing entries, which I suppose is like a lesson about what it's actually like to work on industry networks. But because we weren't allowed to see the terminal that this code was running on, there was a kind of convoluted process where we had to email a fairly senior person at PNNL who would look at the output and kind of give us hints as to what might be wrong with the code. That was a waste of a lot of competitors and a lot of the staff at PNNL's time, in my opinion. And lastly, that finding heuristics that work for almost all networks is very hard. But in reality, the network that an operator is running doesn't change very significantly. So in reality, like network operators do use heuristics. You know, they know which part of the networks the voltage is an issue at, which is why they can get away with like often running a linearized approach. But finding something that works for all networks is sort of, in my opinion, more of an academic problem. And yes, if this has got you excited about the prospect of competing, there's I think they're calling it Challenge 2B event currently on, which invites people to see if they can beat the best scores from Challenge 2 without any limits on time or computation. So, you know, if you have infinite time, what is actually optimal? They haven't announced what the prizes for that will be. I think they're waiting to see how many people actually compete. But there is going to be a Challenge 3, which is currently under development. It's kind of hard to participate without a partner within the US. I mean, you can, but it's hard to actually remain eligible for any sort of grant or prize. But there are some teams that have people working from outside the US. So I'm not a US citizen, so I can't offer to work with anyone, but if you're keen to compete, there are ways. And I think that's all the slides that I have. Yes, questions. Happy to take them now.
Great. Thank you very much, Constance, for this. I thought it was very interesting, actually, when the fact that you commented on challenges that you had issues, what was difficult, what was not. I thought it was very interesting. I will allow though people to, I can see some people are clapping, just for you to know. So congrats. So I will allow people to raise their hands if they want to ask any questions, or you can write them down. I can see Matt. So Matt, go on, please.
So I missed the beginning. My apologies. I was about 20 minutes late, so sorry for that. So sorry. But thanks for the very interesting talk, and congratulations again. I was interested. So just a slightly technical question. I was interested. You mentioned about the calculating the Hessians and things like that.
Mm-hmm.
In textbooks, they always talk about this thing that you only update the Hessian every now and then because it takes forever. Did you implement that, or did you do it every time? What did you find?
So IPOpt has some inbuilt functionality that chooses whether or not to update the Hessian based on how much, like the size, it doesn't do it every iteration. It does it when it does it every iteration at first, but as it gets closer to convergence, it does it less and less often. It depends on how big the step size is, how much it's moving. And I kind of just left that to IPOpt. It was there were lots of options in IPOpt, and I was kind of looking at them and I was like, yeah, I'm going to get time to try all these things out and just tune all of these parameters. But in the end, time was against me, so I just used.
So you calculate the Hessian once and pass it in as like an initialization or something like that.
You pass IPOpt a function which calculates the Hessian for any point, and it chooses when to call a function. So
right, makes sense. Cool.
Great, thanks, Matt. So we've got on the chat box, I can see 2 questions from one of the participants. So it says, I will just read them out. It says, are there some papers published after, I guess after the competition? If not, if you will write some or recommend some papers for us. So I guess that's the first question, is if you've got, I think you've kind of answered, but I will allow you to answer which if you've got more papers, because I think you mentioned it at some point. So, and if not, if you can anyway recommend, and then I will read afterwards the other question. So yeah, I'll allow you to answer this first.
Okay, so I think all the teams have struggled with this a bit with the paper publication, is that a lot of what we've spent a lot of time doing is finding computational improvements.
Okay.
We have published, we've like submitted a couple of conference papers. The person who won, Hassan Hijazi, he had a sort of, he's trying to publish something, and I think there might also be kind of a working paper with some of the other high-performing teams where we compare approach. But in terms of recommended reading, I definitely recommend looking out to see if Hassan gets his paper out. And also something that's interesting is that the RPE has a benchmark team, which is kind of internal applicant. They compete in all the trials, they compete in the final event, but they have early access to all the data. This is called a benchmark because it kind of allows them to like compare, you know, if the benchmark isn't prize eligible, if the benchmark had won every category, they would regard that as a failure, that none of the competitors had beat this one person. But it's also used to check the data before they had these trial events. So he was able to find a lot of the bugs that didn't in the data that stopped them hitting all of the competitors in the trial events. But he is releasing his code as open source. In fact, I think he already has, and he has like a document explaining it. His code is actually really interesting. He coded in Julia, which is an optimization language that I didn't realize has a huge overhead. So his Julia is very fast, but there's like a initialization time, which is up to 2 minutes for really large problems, which when you only have 5 minutes, he didn't do very well in the
It
5 minute division.
Yeah, it doesn't sound so good.
Yeah, but interestingly, so there were 2 divisions, a 5-minute division and a 1-hour division, and his code actually came second in the 1-hour division because once you're over this huge initialization time, it's actually pretty fast. But yeah, I mean, his code is definitely interesting to look at. I can also see the other question.
Oh, fantastic. Do you want to read it out loud for everyone?
Yeah, sure. So if we could do it again, what would we change from the current solution, other coding languages, other solvers, ways to implement algorithms? So I don't think I'd change our coding language. I don't really have regrets about not using C++, mostly because I'm not a C++ expert, and that would have taken me some time to get on top of. Interestingly, almost all of the top teams used IPOpt, so I also don't regret that. And actually, a lot of people are very angry about. There was one of the developers of IPOpt. It's a super old coding language that hasn't been supported for like 10 years. And there's lots of kind of heuristics under the hood. That there was this one of the developers who's like now quite, let's see, he's kind of out of the field now. But he was talking about how, you know, there are other solvers, and like he doesn't understand why people keep using IPOpt when they don't provide support, and a lot of the like heuristics are kind of fudgy. But there really isn't like a faster nonlinear program solver, I don't think.
I also used it in GAMS, to be honest, and I was surprised that other people used IPOpt, because I just, as you said, just played with it one day and I realized it's a good nonlinear solver, but I didn't know it was. I was surprised when you said people use it, because I was like, okay, because I didn't know.
Yeah, the huge downside is like, I mean, it's definitely like takes a lot more time to use it well, you know, because I also use Cplex, again, directly interfacing with Cplex rather than using, and that is definitely more user friendly, but in some ways that's actually a hindrance, because a lot of the like documentation is designed for people who want to run like these small economic problems, and it's sometimes quite hard to tell like what the default parameters are, what's actually going on under the hood. IPOpt is very much the opposite of that, which is good in that it's really easy to tell like mathematically what is happening. But it's bad because there's very little support. I mean, if you are like, there's not much on Stack Overflow, and there's this mailing list that CoinOR like have made open source, where some people ask questions. And again, when I was Googling these IPOpt issues, it was bringing me back to like this thread of mailing lists. But yes, in terms of our approach, the thing I would definitely change was not, all of the winning teams, what they did, well, they're like, let's say the 2 or 3 teams that significantly beat us, rather than just trying to do a kind of mixed integer solver and then this continuous linear program, they relaxed the binary variables to be continuous and did rounding. And we tried this at first, but I guess this isn't really, you know, my background isn't in math, and I just did maths, turned into an American. And I just tried rounding everything at once, and that worked disastrously. But Hassan, what he did was this like really smart batch rounding, where he picked like rounded like variables and then rerun the solution a few times. And I didn't think early on that we'd have time for that, but once we sped up our code, we would have done. And I think that definitely ended up being the approach that worked the best, because like I said, our like linearized approach failed in like a third of the cases. So that was definitely, in terms of an easy improvement in our score, or like a meaningful improvement in our score, that's definitely what it would have been. But like I said, I mean, I was getting the feeling like that maybe we should have explored that more near the end of the competition. But yeah, once we had this event where everyone talked about what they did, I was like, yeah, we really should have explored that more.
It's good though, because at least you learned so many things through this. So I think that's a benefit. I hope Kumpeng is happy with your answer. And now I have seen two people raise their hands. So first was Elias. So Elias, please go.
Yeah, thanks Natalia for organizing, and thanks Constance for this interesting talk. Sorry for joining late. We had a project meeting with Matt. So I just wanted to ask a question around, I mean, you were the first from universities, I remember, right? So like the question is, were there any advantages for research labs? I mean, like institution like Los Alamos was the first. I mean, what are the differences between universities? And,
So interestingly, Hassan, who won, because Los Alamos is where the benchmark team was sitting, he wasn't allowed to enter through Los Alamos. So he entered as an individual and signed a contract saying he wouldn't work on the competition in his working hours. Which makes it kind of incredible that he did so well. I mean, he's like a genius. He's just did it all in his free time. And then the next teams tended to be, they had an academic person on the team, but they tended to be optimization companies were the highest scoring teams. Which, I mean, yeah, that is obviously probably had more people working on it, which I don't think is necessarily like the bigger teams didn't necessarily do better, because there's a sort of trade-off. If there are multiple people trying to work on the same code to a deadline, there are lots of like additional things that go wrong based on being just kind of me working on the code, which I think is exemplified by Hassan winning by himself. But yeah, a lot of the top teams were from this like Global Optimal Technology or Artilis, which are both companies that do optimization. There were also some national lab teams. Some did well, some didn't. And then there were, a handful of university teams. Fewer than a lot of the university teams from Challenge 1 didn't enter for Challenge 2. I think academically, because it's kind of harder to publish this sort of stuff, I think there was a lack of interest. And also, like in the US system, it's kind of hard for a student to work on this for like a year because they have other things going on, and it's sort of not directly research, which I think is why there were probably fewer university teams. But yeah.
How long have you been working on this?
So I joined the team in September of last year, and the competition ended. It was supposed to end in like early June, but they kept pushing it back. I think the final submission was August.
So 1 year, right?
Yeah.
And you were mostly alone, I think. Matt had told me, I think, right?
Yeah, so there was a postdoc who worked in the last challenge, and he was supposed to also work on this challenge.
Okay.
I don't want to say too much because it's being recorded, but he joined another team.
Yeah. It's okay. Yeah.
That's fine. I can stop recording if
No. It's okay.
Okay. Just for the record, I don't mind, or I can cut something afterwards in case I don't know.
Yeah. Congratulations, Constance. Yeah. Sorry, I forgot about that. Yeah. Okay. Yeah.
Thanks, Elias. Sorry, I just want to say it's exactly 5 o'clock here, so I guess it's 9 a.m. there, if I'm correct in terms of, I don't know where you are right now. Is it okay to have one more question? Because there's one more person.
Yep. It's 10 here, but I have nothing to.
Okay.
This, so.
Okay. Yeah. Okay. Great. Thanks, Constance. So yeah, Panayotis, you can go on.
Yes. Hi. Because we have been in a similar situation we have competed in a competition, and I know the computational problems are usually more. Have you thought about using some, let's say, local search heuristics in order to help you create, let's say, a very fast hot start solution?
So heuristics is like an interesting one. In some ways, we did use some heuristics in terms of, removing some things from the problem. We also experimented with a lot of heuristics in terms of trying to find areas which had voltage issues. to like, but I think it's very hard to find a heuristic when you don't have the network yet on like an unknown network. We found that like when we were trying individual networks, we found heuristics that worked really well. But when we tried to find something that worked consistently on lots of different networks, we didn't end up finding.
I was thinking about a hybrid solution, given that you had a lot of computational cores. I thought about, you know, doing some local search based on the outcomes of the, let's say, of the intermediate solution that you are getting from the IP or LP. Probably you could get, let's say, some faster convergence. And so you could add cuts or do some other kind of stuff. You know.
Yeah, I think definitely, I mean, there were loads of things I wish I could have had time to try. And yeah, like a lot of teams also didn't fully exploit the computation time we were given, because we could run sort of 6 things in parallel, but that wasn't, we didn't really have time for Bender's decomposition or any, like actually decomposing the problem. So a lot of people ended up, I mean, we used 3 of the 6 processes for just having backups, but a lot of people kind of interestingly were trying like fixing different things on the different parallel runs.
Okay, just using parallel runs usually doesn't help. Okay, as you can see, I'm from this world, so usually it doesn't help. You have to somehow coordinate them and be able to.
Yeah.
Interesting information. That's.
Yes, definitely. There were lots of things that.
So what you would propose someone that wants to go for a MOM challenge?
Well, that is actually, it's really interesting that they've just removed this like computational time barrier. I would say that like the winning team, I mean, and I haven't decided if I have time to enter. So this might be, I'm not withholding advice because
Because we were thinking about joining, but okay. I don't think also we have time.
I think that that because they're removing this barrier, like the winning teams will be the ones that like actually pursue like complete optimality. I know that Hassan had developed like a kind of relaxation to the problem, which he wasn't able to implement in time. My guess is that he's going to win this again by like, because I think he's been working on it in the meantime. But I think it will be, I think also it would be interesting to just use heuristics to maybe with these cheapest generators, just like run with the cheapest generators. And if that doesn't work, like try like individual switches. I think if I were to enter, I might pursue something like that.
Thanks.
Great. I don't know. I don't think we have any more questions right now. I don't see any other hands. Okay. I guess Constance, I don't know if I can ask a last question. I don't know if you answered that already. You mentioned a couple of times that they did not like this decoupling that you guys did, and that many teams did it because of course you said computationally you guys couldn't do anything else. Why is it that they didn't like it? They wanted one thing, everything. Is that?
Yeah, I think because we kind of weren't solving SC-OPF anymore. We were sort of solving like 2 sets of OPF.
They didn't like that. Okay.
I think they wanted us to like pursue like an actual SC-OPF solution. Yeah. But I mean, that was a mistake in terms of the like way they scored it. And I mean, in the event they were talking about so your score was the combined score of like the cost of your base case solution and the average of your contingency scores. And for the networks where there were thousands of contingencies, like one bad contingency score when in the average had very little effect. So they were talking about like, would it have increased coupling if it was the score, just the worst contingency score is like the second half of your score. And definitely that would have forced people to try and, I think what they wanted people to do was to filter the contingencies and to try and predict which were the like 2 or 3 really important ones and include those. That's what kind of happened with challenge 1. And that's what we assumed we were going to do. But when we started including what we knew to be the most important contingencies, we found that it made almost no difference to the score. So yeah, I think they might come up with a different like evaluation method for the next round.
Yeah. No, that's very interesting. So thank you very, very much, Constance. I can see people saying congratulations as well. And thank you very much. So thank you so much for this presentation. Thank you everyone for participating and for being here, and see you all next time.
Yeah.
Thank you so much.
Thanks, Constance.